Here are the custom limit switch PCBs that I designed, and I had these made by JLC PCB. Quite a lot of them because there's a minimum number of panels and a minimum number of a minimum panel size, so I ended up with 160 of them. Mostly I don't need those. They're quite simple, apart from that one little bit that's missing. You'll see that's the optical sensor itself, and these are a little bit expensive and I didn't want to put them on all of them here, so I just bought this separately on AliExpress and soldered them on manually. The reason I did this instead of just buying some ready-made sensors is I couldn't really find any that weren't kind of big and clunky. At least they would have looked a bit out of place on my machine, I think, and I wanted to keep everything super light and compact, so that's why I went with this. And this is what they look like when the optical sensor is soldered on, and some pins. I'm not entirely sure that the circuit I designed here was a very good one, by the way, so I'll put that on the screen and maybe somebody can tell me if I should have done something better. And here's what they look like when they're installed and powered up. The little green LED is to signify that the beam has not been broken. And to break the beam, I first tried just using a little piece of cardboard. It's just double-sided tape stuck on there. But the cardboard unfortunately was too white and transparent, I guess. So I had to put a little piece of aluminium can on the side there, which is what those pieces are. And that does cause the beam to break fairly well. There's another one back there, by the way. Unfortunately, these little LEDs, they don't turn off at the same time as my Linux CNC detects the beam being broken. I think that's a problem with my circuit. The transistor requires a slightly different voltage to what the LED does to switch. For my air valve switches, I'm going to try using these really small solenoid operated ones. See, they're quite small when I put my finger next to them. And I'm testing with this hand operated vacuum pump, which is quite convenient just to give us a little bit of vacuum like that. And I've checked both ways, and these valves, they don't seem to have any problem holding up to minus 80 kilopascals in each direction, which is about all I need, I think. There is a slight leak somewhere in this. I think this thing is leaking sometimes, so I'll have to be quick with my next little demonstration, but just have a LiPo with about 12 volts roughly on there, and I've put I think it's a 27 ohm resistor just to make sure that the solenoid wiring is not taking that 12 volts the whole time, because one of these solenoids will have to be open for quite a while, the one that does the picking, the actual suction on the nozzle to lift apart. Most of them only open very briefly, but one of them will have to be open for a while. So anyway, I'll just see if I could touch that on there, and we'll... Oops, I touched it twice, but you can see that it works. Just in case anyone's playing along at home and thinking of using these valve solenoid things for themselves, I'll just point out a couple of things. This is the 27 ohm resistor that I was just using. With that in series with the solenoid at 12 volts, it gives me about 76 milliamps, which is a little bit too close to the 80 milliamp rating for the solenoid. So I changed it to a 100 ohm resistor, and that keeps the current to about 50 milliamps, which is a lot better. However, I found that it's not strong enough now to open the solenoid if the vacuum is on the plastic side. The vacuum is on the steel side. See these? One side's plastic, one side's steel. If it's on the steel side, you'll be okay with a 100 ohm resistor still. Here's an overview of the vacuum system that I'm planning to set up. It should be mostly self-explanatory, I think, so I'll just let you pause the video and look at the details. But I will just mention why I want to have two different reservoirs. The main reason is because I'm going to use a refrigerator pump to provide the vacuum, and that's not supposed to be turned off and on too quickly. So we want to have a large reservoir that only needs to be refreshed occasionally, and that's going to have a stronger vacuum. And then this smaller one will be positioned closer to the machine, so there could be quite a big distance. Like this large reservoir could even be in a different room, but the small one will be close to the machine, and it's going to maintain a much tighter range of pressure, possibly minus 50 to minus 40, something like that. But this one will be able to top itself up from the other reservoir
much more frequently. So the idea being that we can keep a much more consistent vacuum every time we want to try and pick apart. It's not going to be in a range of, say, 20 kilopascals difference each time. It's just going to be maybe 1 or 2 kilopascals different each time. So it should be more consistent. The other thing I'll mention is I've got this valve over here and I've written normally closed, opens briefly to ambient pressure for blow off. So this is when you put the part down and you want to let it go. If you just close this solenoid valve here, there still might be a little bit of vacuum in this tube here, and the part might still stick to the nozzle when you lift it up. Apparently that's not a big deal. Most people say that doesn't really happen that much, but what you can do to make sure of it is open this pipe to the ambient air pressure, or better still, provide a little bit of positive pressure to actually blow the part off as the nozzle lifts up. And so somebody told me I don't really need to have a second solenoid valve here if this one was a three-way one. So this could be one that opens to this side, or it opens to ambient, and it could all just be done by one thing. But I don't have any of those three-way valves. I only have two-way valves, so I'm just going to use the ones that I have. And in future, if I do want to have a little bit of positive pressure here, then I will need this other valve here, so I'm just going to include it for now anyway.
For vacuum sensors, my first thought was to try the MS5611 barometer, because I've have experience with using that in the past, and IO Mixer already supports that, so I was thinking maybe I could use IO Mixer to do some vacuum regulating. But I found these things on AliExpress, and they're quite cheap. I think they're about $7 New Zealand dollars, and I forget the exact model number, but that number there is part of it. I'll put the full model name on the screen for you here. And I was a little bit concerned since I hadn't had any experience with these, and typically that means that it might not work out how you hoped it was going to, but I gave them a try, and they're pretty nice actually. They're giving me about 150 Hertz update rate. And another attractive point is this little plastic nozzle on there, which fits perfectly in these little silicone tubes that I'm thinking to use. So I have one of those set up here, and it's going into, well, just going into this vacuum pump. So I can get positive pressure on this by squeezing and hopefully sealing off the tube there, and then rolling my fingers a little bit to the left like that. And I can get negative pressure with the pump itself, of course. And for testing purposes, this is connected to, well, it's an IO Mixer board, the hardware is, but the program that's running on it's not the IO Mixer firmware. It's just a little test program that I wrote, and it's just outputting over a UART connection to my computer. And we can see the number here. This is the number of kilopascals that it's sensing. So it's about 0 at the moment. This is relative to ambient, outside air pressure, of course. But if I squeeze that little tube, and then it's a bit tricky because you have to seal, you have to make sure there's a proper seal, and then squeeze and roll your fingers to the left. And I'm not going to be able to do it very well, but you can see some positive numbers there, 5, 6, 7, 8 roughly. And if I let go, it just goes back to 0. And then if I squeeze the vacuum pump, well, the sensor can go to minus 100 apparently. That's what it's supposed to do. But this, if I pump this pump a whole lot, I can only get it to about 82, I think is the lowest, or 84, there we go. And then if I touch the release valve on the pump, it goes back to 0. So I think everything is working quite nicely there. And this is a little graph that I made earlier just by copying and pasting some of that text into a spreadsheet. And the one on the left is where I did the little squeeze thing to get some positive pressure. And then these two here, I just sucked on the pipe a little bit to get some negative pressure. I was just curious to see how smoothly updating it is, because we're getting 150 values per second, and I was curious to see if they're actually different values. They are. So if I just stop that update for a minute, sorry about the shakiness, but if I stop that there, you can see they're all actual unique values, so it's not repeating anything. And then when I graphed it, we get these pretty nice smoothly updating curves like that. So I'm quite happy with that for the $7 or whatever they cost. It's not much. Okay, I added support for this sensor to the IO Mixer. It's the one at the bottom there, XGZP. I might change the name of that sometime because it's not really that clear what it does. But anyway, if I squeeze my vacuum pump here, let's see if we can get it to 84 again. Oh, 85, okay. And if I just let it off, when I set this machine up, I want to have the vacuum solenoid riding on the head so that the vacuum can be brought as close as possible to the nozzle, and there's just going to be a short, maybe 20 centimeter section of pipe between the vacuum and the nozzle, so that the volume of air that needs to be evacuated is as small as possible, and the vacuum will take effect as quick as possible. But I don't really want to have this vacuum sensor riding on the head as well. Oh, sorry, the sensor there. Because that's just going to require more wiring and everything to go up to the head. So I thought I might try and have this sensor way back, you know, with the other stuff near where the Raspberry Pi is. But it's going to have to sense the vacuum in a rather long pipe. I've got a pipe here that's about 1.5 meters long, I think. So I'm just sort of curious as to whether that would cause any delay in how the sensor detects changes in pressure. It doesn't really seem to. This pipe's very small, so the overall volume that's inside it's not that much. But the way I've got it set up here is that when I go, or when this meter goes over 300, the LEDs on the I/O mixer will turn green, like that. And when I let it out, I mean, the I/O mixer is only running at 50 Hertz anyway, so it can't go faster than that. And I'm not able to determine with my human eyes whether it's slow or not, so I think it's going to be okay. Let's try that again. Ready, go. I mean, it's not really a very good test, I suppose. But the thing is, the I/O mixer, like I said, is only running at 50 Hertz, but when I get this running on the Weenie PRU, that's going to have to connect to, that's going to be running at 1000 Hertz, so we'll be able to use the full 150 Hertz update rate of the sensor. To create a vacuum, I'm going to use this old refrigerator pump. I got this on Trade Me a few years ago. I was originally going to use it for vacuum bagging, but ended up not really using it. The main reason was because when I got it, it didn't have this capacitor and this PTC relay thing on there, and despite having a model number prominently displayed here, there's precious little information to be had, so for quite a while I wasn't really sure what I needed to do to get this running, but eventually I figured it out, I think. Seems to work anyway. Bought these separately off AliExpress, and hopefully everything is okay. I ran it for about 10 minutes, and I used my little thermal camera thing to check that nothing was getting too hot or anything. And to make a vacuum reservoir, or two reservoirs actually, I'm going to use this large piece of PVC pipe. It's a little bit larger and more sturdy than I needed probably, but I bought this a few years ago and it's been sitting around. Surprisingly expensive too, so I'm glad to finally be using it. So I'm just going to chop that maybe about here to make the smaller reservoir and the larger one from the rest of it. The reason it's so large, by the way, or why I'm okay with it being so large, is that the refrigerator pump, it's not supposed to be turned off and on frequently, so you don't want this to be turning off and on every, say, 60 seconds or something crazy like that. They're not really made to do that, and I think part of the reason is that the way that PTC relay works is when you turn it on, initially it's in the circuit, or it brings this into the circuit or something, and as it warms up, it gets to a point where it gets too hot and then it turns off, and then after a while it will cool down, I suppose, but you don't want that to be getting too hot. Well, I'm not entirely sure what's going on with this PTC relay thing, to be honest, but anyway, I read somewhere that these are not supposed to be turning off and on too often, so the larger a reservoir you have over here, the better probably. And to close this up, I just have some of these, again, PVC things that will go on the end, and I'm going to glue those on with this nasty PVC cement. Works quite well. And for my fittings, I'm going to use these little garden sprinkler attachments. They're just quite small, so they fit on my silicone tubing quite nicely. So these little garden sprinkler things are a perfect fit for a 4mm hole in here, and you can sort of screw it in even. I'm not sure if this is threading the hole or if this harder plastic is just crushing the thread on there, but either way it fits in there nice and tightly, and a little dab of that glue should make it nice and airtight. And on the vacuum pump here though, it's quite a bit larger. This is 8mm pipe there, and it fits perfectly on whatever size of silicone tube this is that I'm planning to use. Perfect fit. But I was wondering how I could, you know, make a nozzle or whatever to stick a larger thing on here, and then I remembered something. That's right, I have a lathe. Here's how that large fitting turned out. Unfortunately, I made that hole a little bit too large, so when I put this in there, there's no grip or anything at all. So I thought it might be wise to put a couple of little self-tapping screws into the sides of it like that, because I'm probably going to have to pull on this hose quite strongly to remove it, maybe. And then to stick it on a little bit better and also to make it airtight, I'm going to use some of this liquid electrical tape, because there's no way it's going to be airtight just like that. Last time I used this was actually on a similar sort of a thing. It's like the old vacuum pump that I made. It turns out it's held up very well. 3 years or so it was that I used it, but it's holding up very well, and it also sticks to the PVC very well. And it's a little bit rubbery, and it fills the gaps, and I think it'll be okay. Uh-oh. Probably should have just used liquid electrical tape for this one too. Oh yeah, this is much better. See, when I was using this one, the threads of the thing that I'm trying to screw in were just dissolving. Okay, I'm just doing a little test to check if there's a proper seal around these joints here, mainly is what I'm concerned about. So I joined that together into one T thing. Also I wanted to check how well these seal for a vacuum. And it's been holding about 300 millimeters for 10 minutes, so seems to be good. There's two types of silicone tube here I have. One is a very thin wall, and there's this one which is a thicker wall. Looks like that thin wall one, it's just too soft. So this wall is quite thin like that, see? Especially when you want to turn around a corner like this, it just seems to be getting squashed in by the vacuum. Okay, I've set up one of these IO mixers to function as a regulator for the refrigerator pump, and I've set the limits to be from minus 60 to minus 30 kPa just for this test. And you can see it's at minus 40 at the moment, and there's a slight leak. I'm using that manual vacuum pump again. I think there's a little leak around the valve somewhere. Anyway, when this gets to minus 30, we'll see a little blue LED turn on, which means I need to do some pumping, like that. And you'll also see on the right-hand side the LEDs go red to signify that the pressure is too high. So I do a bit of pumping. Whoops, went a little bit far there. So we've just gone over minus 60, or under minus 60. The purple light here means it went a little bit too far in the other direction. But anyway, the blue light turned off, so I stopped pumping. And that's what would happen in the normal functioning of things. But I also wanted to use this I wanted to make sure the refrigerator pump didn't run for too long. So this time what I'm going to do is I'm going to pretend that there's a leak in the vacuum system, and when it gets to minus 30, I'm not going to pump. And you'll see there's a timer counting up, and when that gets to 10 seconds, just for this little test, the pump will turn off, the blue LED will turn off, and this other one, the red LED, will start flashing. So the idea is that I'd have some sort of an audible alarm to let me know that something's wrong, because I don't want that pump to just keep running and running and running. And it's very quiet, and I'm thinking to put it in another room so that I can use a different wall socket to run it. And if I do that, there's a pretty good chance that it could just be running and running, and I wouldn't notice it because it's so quiet. So this is a reason I would want to have an alarm to stop it. And to do the actual switching of the pump off and on, I'm just going to use one of these relays here. They're quite cheap, and they can do pretty high voltages. Oh, it just turned on. Well, you can see it turned on there because it got to minus 30, or below minus 30, and then if I pump it a little bit here, you'll see it turns off. Alright, just doing a little test to see how much vacuum this pump is capable of pulling. So the IO mixer is connected here, but it's just to show the pressure in the chamber. It's not controlling anything. I'm just running that from a USB power bank. So this relay over here is doing nothing at the moment. And on this side we have our connections like so, the large tube is going into the pump, of course, and it's just hanging on there by about 2 or 3 millimeters of contact there. But the nice thing about a vacuum system is that it all kind of clamps itself closed nicely for you. And then you can see these ones, it has vacuum in there at the moment. You can see these tubes have got squashed, but it seems like there's enough here still going through that we can use the IO mixer to sense it properly. And then there's a T-joint there. This tube is also crushed. But the nice thing about all this is it very, very easily made it to minus 80 kilopascals of pressure or vacuum, and it did it in about probably 30 to 40 seconds, maybe less than a minute, I'd say. So I'm really happy with that, and I'm also really happy with the fact that it seems to be very well sealed. 6 minutes ago the reading was negative 80.2, so now it's negative 79.8ish. So there's maybe a tiny leak somewhere, but in the overall big picture, that's really nothing. To put that relay in the mains circuit, I just cut a little bit out of a extension cable like that and took one of the wires out there. Okay, so everything's connected up, and I'm just going to turn the IO mixer on. There's no pressure or no vacuum in the system at the moment, but I just wanted to show you how quickly it gets to, in this case it's going to be minus 60 is the setting. There we go. It doesn't take long at all.
Let's have a look at the configuration that's running on the IO mixer to make that happen. This is the core of it here. I think we'll just look at this bit. It starts with a pressure sensor input. This XGZP I think is the family of sensors, so I've just called it that. There are other ones that measure different scales of pressure, but the one that I'm using, if you give it a scale of 65536, that will get you a value in kilopascals. And the green display node there will just show that on the little mini LCD screen. By the way, these nodes are all connected like that with these wires, but I found that if you give your nodes nice names like this, so that each one is, has some sort of a description of what it does, you don't really need all these wires all over the place. They just sort of clutter things up. Anyway, we have a couple of comparisons here to figure out whether the current sensor reading is either too low or too high versus the limits that we've set for our desired range. And then we can take those to do another binary operator. This time it's an OR. So we're checking if the current reading is either too low or too high. And then over here, this store value doesn't change every time. It only changes sometimes. So if the pump was already running and it's inside the range that we want, we just leave it running, right? And if it's already off and it's inside the range, then we leave it off. So we only want to change what the pump is doing when it goes outside the range. So that's why it has this allow changes is being determined by this condition there. And when it's outside the range, we want to turn it on if the pressure is too high. And then if I just turn those wires on again, we'll see that this is the main output condition of our system, but there's a few other things that we need to do. We'll just follow this through here. So this pin here, pin 36, is the one that's connected to my relay that switches the main circuit. So this is the overall output that's going to turn the refrigerator pump on there. But as you can see, there's a few more conditions that we need to take into account. So we've decided whether we want the pump to be on or not, but we also have to consider whether the alarm is going on.
Oh boy, I just had one of the most frustrating debugging sessions I've ever had. I was just adding support for the Weenie PRU to use one of those vacuum sensors there. So that's a vacuum sensor and it's connected onto here, and that was actually fairly easy. But I discovered along the way that my limit switches that I set up a few days ago, which were working perfectly, were no longer working. This little piece of white cardboard here, it turns out that wasn't enough to block the light well enough, so that's why I've stuck a little bit of aluminium can on the end. And aluminium does block the light quite well, so when we push this through there, you'll see that turns off. And that one is working, and when it switches the limit switch, we'll see this is the RGB LED strip underneath. I just put a piece of paper on top so you can see it a bit better on video. The green light just means that the machine is on. The blue light is the one that we get from the limit switch. So if I just move that back a bit, so that's that axis. And originally none of them were working very well, even though all of them were perfectly fine the other day, and I just couldn't figure out why, because I hadn't changed anything. So anyway, after much investigation with the voltmeter, I realized that my pull-up resistor that I have on there, these are some that I have yet to change, but you can see between the S and the V there's a little resistor soldered on there. It's a 10K, and turns out that's just too high, so I changed that to a 2.2K, and then the one at the back has been working beautifully. These other two still, for some reason, so they all work the same. They all have a little piece of aluminium can, and they're supposed to block it like that, and then this one goes up into there. So we should see two blue lights over there. We've got one, which is better than nothing. I was expecting to see none, but as I was fiddling around with things, I discovered that if I just sort of approach it with my hand a little bit like that, not touching it, just sort of waving my hand around in the general vicinity, you can see one of them's actually behaving itself quite well. Usually both of them are off until I wave my hand around near them. So naturally when something like that happens, you think, oh, it must be a bad connection, or in some way the voltage potential that's on my hand and coming close to that is making just enough of a difference that the transistor that's on there is able to switch properly. And anyway, to make a long story short, I finally realized what the problem was, and this also explains why it wasn't a problem the other day. Do you see the problem? Let me show you how to fix the problem. Let's pull the curtain a bit. Oh. Remember, these are optical sensors, right? So let's go sideways. Now look. Working beautifully, and then up and down. Up and down. So that's it. I guess the optical sensor inside those things is supposed to be encased inside some sort of a enclosure so that you can't get like strong sunlight on it. Well, not that there was strong sunlight, but it was enough to make a difference. So that also explains why it was not a problem the other day, because I was doing it at night. So the only light that was on it was just the light in the room, which is not strong enough to affect these, I think.
Okay, now that the Weenie PRU knows how to read one of those vacuum sensors, it can relay that reading to Linux CNC, and we'll be able to see that here. If we look into pins, Weenie, and there's a new one here called pressure. There's just one at the moment, possibly more in future maybe. But when I click on this, you'll see a value approximately 0, and if I click on it again, you'll see that these values are changing a little bit. Or if I do this, click on watch and then click on this again, there we go. So we can see those values updating live, and if I squeeze my little manual pump thingy, we'll see it going into the negatives, negative 50-ish, there we go. And if I release that pressure, back to 0, perfect. So there's a couple of things that we want to use this vacuum reading for. One is so that we know when the smaller reservoir is running out of vacuum, and we need to open the solenoid valve between the two reservoirs so that the larger reservoir can replenish the smaller one. The other thing we need to do is use this to detect how much pressure there is behind the nozzle, because sometimes when we try and pick up a component, we might miss it and it doesn't get picked up. And in that case, we'll be able to look at this pressure reading and see that the vacuum's not built up properly, and we'll know that we need to, try and pick up again or sound an alarm or something. And my first thought for what to use to control this would be some external system that just looks at this number and does the solenoids externally. But then I realized that it's not that complicated, and Linux CNC could probably handle this entirely within itself using a component. So I think I'm going to have to explain what components are at this point. This is a picture that I drew of a component, and you'll notice that it doesn't really have any distinguishing features, and that's because components can be just about anything. It's basically a little bit of C code that you can quite easily set up as like a plugin. It makes Linux CNC very powerful and extendable. So what's in here could be, like I say, anything. And in fact, the Weenie PRU that I'm using to do all this is itself a component. It does a whole lot of things. Like we just saw, it's reading the vacuum sensor, right? It's running the stepper drivers. It's running the LEDs. It's looking at analog inputs. It's running SPI connection to the Raspberry Pi. All of that stuff is in one component. Now, the component that we're going to make here is not that complicated at all. So let's just look at a very, very simple component. Probably the simplest one I can think of is a component that just takes the input, a Boolean value, either true or false, and it just returns the opposite. So that would be called a NOT. And if we were to give some names to the inputs and outputs, you can have multiple inputs and outputs, of course, but for this simple case, we just have one. And we might call the input in and the output out, like that. And they need to have a global name, all of these things. So if you have more than one of these components, more than one of the same type, you need to give them a unique name. So they'll end up being called not.0 and not.1. And then the inputs and outputs will have that prefix respectively, like so not.0.in and .out and so on, like that. And as for how to configure these nodes, oh, did I say nodes? I mean to say components. But you might be thinking that that little picture there reminds you rather a lot of these nodes that the IO Mixer uses, and in some ways they're very, very similar. We've got inputs and outputs like that, and they get connected together. In IO Mixer we connect them together nice and graphically by going like that. But you could consider also that this wire here, in Linux CNC these wires are called nets, and a net will connect some inputs and outputs. And the way you do it in Linux CNC is you just have a text file, and you just put the name of the output and the name of the input on the same line in a text file. So it's a little bit more primitive, but basically it's kind of achieving the same thing. So let's have a look at an example of how some NOT nodes might be configured. This is the actual HAL configuration. So this stuff goes in the HAL file for your Linux CNC setup. And I've highlighted 3 examples of where I've used a NOT node. And the reason I'm doing that is because for my limit switches, when the limit switch is touched, or like when the axis gets all the way to the end, it's going to give me a negative output. And when there's nothing touching, it gives me a positive. It's kind of the opposite to what I wanted. So what I've done here is I've just taken my Weenie inputs 0, 1, and 2, which are my limit switches, and I'm passing those, or I'm connecting those to not 1 in. So it's like, well, it'll be this one here. So my limit switch is coming in here. It's going through this not, so it's just being reversed, switch from true to false, or vice versa. And then on the outside, we have this not 1 out, like that. And so not 1 out is on another line because it's connected with a different net, or a different wire, if you want to use this terminology. And then that's going to go on to do all of the stuff that the limit switch needs to do in the system, which is the rest of it there. So as for where you can get these components from, if you want to use the existing ones, you'll probably find yourself looking at this HAL component list page, and there are an enormous number of them. Mostly the ones that I was interested for this particular job were these logic ones, and there's also some arithmetic ones like that. So for example, this one was very interesting. You can see I've clicked on that one. Comparing 2 inputs with hysteresis. Sounds like just what we need. Unfortunately it wasn't. It doesn't quite do what I need, but I'll just click on that and look at the help description. So each one of these tells you what pins there are, so you have in and out pins and so on, and some other parameters and a description of how it all works, which is very nice. But unfortunately I probably could have used a collection of some of these to get done what I wanted to do, but it would have been quite clunky, and this text file would have had masses of lines in there that just didn't seem, just didn't really fancy doing that. But I discovered you can make your own components very easily, and you can do it with this thing called the HAL component generator. And you'll set up something like this. So this is a simple component example. Yes, that's the whole thing there, like that. And then, yeah, obviously you've got to follow this formatting, which is described on this page as well, like how to set it up with all the syntax and stuff. And if you go all the way down, there's some more examples of how to use things there. And when I saw this, I thought, okay, I will try making one of these. So I'll just show you the one that I made, if I can find that. And I've called this T-stat, which is short for thermostat, because the function that it does is sort of similar to how a thermostat controls temperature. And it's only one way though, so it doesn't do cooling and heating. It only pushes the set point, only pushes the value in one direction towards the set point. Yeah, so I don't think I'll explain this because I'm not a pro at it, but you can see we've got some inputs and outputs there. And this is the function. So this bit here is basically, this is C code. And it just lets you use variables that you've declared in this little bit at the top, which is not C. This bit here is just some sort of special script that this HAL component generator uses. And then it's a little bit like Arduino, really, isn't it? Because we've got this setup that you can do at the beginning, and then you have like a loop function, which runs every time it gets called. And then you compile that by running this here. You do HAL compile, and you can either install or you can just compile if you just want to check that it's working. You can do that. And then you just give the name of that comp file, which is this one here. And there you go. You have a component. So if we go back to our Linux CNC on here, we'll see that there's a T-stat component, because I've already done this, of course. And if we look at the T-stat, we just have one of them. And if I expand that, we can see some of the things that we saw in the text file there, if I can just get that back. So we have active, enabled, in range, max, min, and value. So that's these things here that I've declared in that bit there. Some are inputs and some are outputs. And the reason that's there, though, is because I put it in my HAL file. So we have to go back to this file. There's a bunch of settings all over the place. But so this set of lines here is how I've created an instance of one of those components. And it's called tstat0. And I've connected the value. So this is an input for the component. I've connected that to my weenie pressure.0 that we saw before. And for this test, my limits or my range is from -40 to -20. Enabled is true, and the reason we have an enabled is so that we don't want the smaller reservoir to be getting replenished from the larger reservoir in the middle of a picking operation while we're trying to carry a part around, or we're trying to detect that the vacuum failed or the pick failed, for example. We don't want this to be happening in the middle of that, because it would mess up our determination of whether the pick failed or not. So during a pick, this enabled is going to be set to false, so no small reservoir replenishing is going to happen. And then decreases is just an option to say whether the value is going to increase or decrease when the pump is on or the heater is on or whatever. So if it's heating, it's going to be increasing. If it's cooling, it's going to be decreasing. And so this needs to know which way the action is going to occur. Anyway, so the reason that we see this T-stat in here is because I've put these lines in this file. There's actually a little bit more. So this T-stat0 doesn't exist just out of the blue. If I scroll all the way up to the top here, we'll see that I had to also do load RT, load real-time component, T-stat, and I want one of them. So you can give a count of more than one. For example, see I've loaded not. That's how I got those knots. And for knots, I'm using 4 of them. For T-stat, I just need 1. And then down here, we also need to add this to the servo thread, so that this is going to be happening 1,000 times per second. At least in my case, it's 1 kilohertz loop. So that's where that T-stat comes from, all the way down here. And let's look at the result that we get from it. So let's look at the value. And we can see that the value is the same as weenie.pressure.0 because they're connected together, right? That's what this line here does. It connects those two values together. And we also want to look at in range. Look at that. So this red means it's false, so it's not in range. So remember our range was minus 20 to minus 40, and it's not in that range. And then active, yellow means it's true, and that means that the pump or the solenoid valve is going to be open. So let me do a little bit of pumping here, and you'll see that when, whoops, I went a little bit too quick, but you can see that now we've gone below minus 20, so in range became true. Active stayed true because the goal of this is to bring it to minus 40. So let me pump a little bit more. I'll try and go slower this time. So when I get to 40, minus 40 rather, we'll see that they both go off because we're no longer in range, and the pump should no longer be active because it's already created enough vacuum. And while I was talking there, we'll see that it went above minus 40 and we've come back to in range. And if I let some pressure out, when it goes below, when it goes above minus 20, we should see active come on again. Try and do this slowly, it's a bit hard. There we go. Alright, so now the pump, sorry, not the pump, the solenoid valve needs to open again, and in range is false. So it looks like this entire thing can be controlled completely within Linux CNC as a component. Isn't that cool? What a great system. So to connect the output of that component to something in the real world that we can actually control, let's just finish that example properly. What I can do here is I can put another line in my HAL file that says tstat0 active. Remember, active is the final output, the decision about whether this vacuum solenoid should be on or not. And I'm going to connect that to weenie output 0. So this is a digital output. It's just a pin on the weenie PRU that's going to turn high or low. And I've also connected that to one of the RGB LEDs. In this case, it's the 5th LED, and it's going to turn the red component of that on when the vacuum solenoid should be opened. And this is the result of that. The red light there signifies that the solenoid should be opened. In this case, I'm just going to use this pump to pump some vacuum in, or out rather. And digital output 0 happens to also be connected to that little blue LED, so we can see that changing as well. And on this meter here, you probably can't see it very well, but there's a mark 300 there, right about there, is when the system should recognize that there's enough vacuum. And so the red and the blue LED should turn off right about there. And as we let the pressure out, when we get back to about halfway down there, then they should both come back on. It's a little tricky to do this slowly, but right about here, they both come back on like that. So, seems to be working. To perform the actual switching of these little solenoids, normally I probably would have just taken a MOSFET like that and soldered up a quick and dirty Mickey Mouse connection of wiring to get it done. But I was looking around in my drawers of old projects, and I realized I had quite a few of these little switching boards that I made years ago. I was actually making a system for testing lithium-ion cells, the 18650s mainly, but I didn't really know exactly what I was doing with the switching and the gate driver and stuff like that. So this I made as a preliminary test from JLC PCB, of course, and I just wanted to make sure I was getting the high power MOSFET switching part of it right. So it's got this gate driver that I'd never used before, and I just wanted to make this standalone piece to check that this subsection of the circuit was okay before I put it into a larger piece. Anyway, so it's going to be quite handy now, because even though it's way overkill for what I need, we only need, I think, about, what was it, 70 milliamps or something like that? This can handle 3 amps continuous easily, probably 4 actually, now that I think about it. But anyway, I'm just going to put my 12 volts on here, and then it's got this nice couple of little connections there where I put the ground and the signal from the digital output that we were just looking at, the little blue LED one. And then on here I'll put one side of the voltage that's coming in to power the pump, and that will, not a, I keep thinking I'm talking about pumps, but it's a valve.
And so this thing will switch it off and on for us. Okay, so I finally put everything together for the first time, and I'm pleased to say it works great. This is obviously not where it's going to be permanently, it's just for testing, but let's have a look at what we've got. So we've got the mains power coming in here, going into this, and this is just going to be powered from the power bank for now, but obviously I'd like to power it from like a USB power supply that's running off the mains as well. And then it's pulling air through there, which is coming into here, and then it's just using that one for the sensor on there. And the setting for this is -60 to -80 kilopascals. Then on this side we have the outlet going through the solenoid valve to the smaller chamber into there, and then on this side we have a T-junction which goes into this thing, which I can use to see the pressure on this side, and there's a little valve here which I can use to let air out. And the other side of the T goes through all that pipe over to the sensor on the weenie PRU. So this is heading for -80, and it started from nothing, so it will take a little bit of a while to get there. Anyway, so that'll get to 80 and turn off in about 10 seconds or so probably. And we can see these tubes here are starting to get crushed. So that's squashed in. But this one on this side is not squashed in yet. But, oh, okay, so that pump just turned off. We got a purple light, which means we went a little bit too far, but that's all right. And then over here we turn this switch on. And you can hear there we go. So about 300 on that inner meter is where it's supposed to be going to. And if I push this quite strongly, I can get it to go immediately below the point, the set point, and then you can see it's just running, just holding that solenoid open just a little bit. If I do a big press, then we go, it'll take longer to recover. And it seems to take quite a while to exhaust the supply in the large reservoir. So we'll do a whole bunch of it, and then we'll see what the large reservoir is at. So it's gone from -80 to -60. And this is going, oh sorry, this is going to -50. So it won't turn on the fridge pump again until we do quite a bit more. There we go. So now this is running again. And it stinks too, because it's pumping air out of here, which came from inside there, and it smells like that PVC cement. It really stinks. But everything is working great. Yeah. By the way, if anybody was looking at the way these mains connections are kind of exposed and cringing at how dangerous that could potentially be, allow me to validate your concerns by admitting that I got a shock of this just before. Not quite sure how it happened, because the only thing that's exposed, so what I touched was just under there where the blue wire is going in, and I touched, I guess, where the blue wires, like those pins on the bottom, right, are exposed. But I wasn't touching anything else. There's no way I could have touched the rest of it. So I don't know why, I don't know exactly how that shock worked. And fortunately it just seemed to be mainly in my fingers, these two middle fingers. They still feel a bit weird. But yeah, how does that, how did I get a shock off that? I don't get it. Was it just that the potential between the blue there and just the general surroundings here, where, like, you know, everything else here is at such a different potential that was enough. I don't know, but I will definitely be enclosing this and that bit there. We're not, because this is mains voltage up there too, right? It's not plugged in now, by the way, so don't worry about me waving my fingers around it now. But yeah, this definitely has to be improved for safety's sake. Oh, it's perfect. Okay, I finally managed to make one of these nozzle coupling adapter things that I'm happy with. Took me quite a few attempts. Those are my fails, so this is the fourth one, and part of the reason is that I'm new to using a lathe, so not very good at it, and this is actually only the second thing that I've ever made that's an actual part that I want to use. The other thing is that it needs to be quite precise. You want to have as little run out as possible, and it's got this slightly complicated fixture in there. So you need a 5mm thread halfway in, down there, and then you need 7mm around this bit. That actually turned out to be the easy part. I thought that would be tricky. The difficult part was this hole on the back. This has to be 5mm, and if it's slightly big, when you put it onto the motor shaft, which is very, very short, it's only 5mm, so you need to have it quite precise, otherwise it's going to wobble like that on the shaft. So I first tried with a 5mm drill. That was not going to work. I think my tailstock's not quite lined up properly. So I ended up making a tiny little boring bar out of an old drill. And even then I still needed another 3 tries, because it seemed like you have to go super, super slow. And I thought I was creeping up on it real slow, but then all of a sudden it would be too big. So on this one I finally figured out what was going on, because I was mounting this in the lathe to then be able to screw that on, and then to check it I'd take it off and check it with the motor, of course, and then I'd put it back on and do a little bit more cutting. But what I forgot was that when I put it on, just the act of taking it off and putting it on again would slightly change the position. So instead of adjusting my dial on the lathe and then doing another cut immediately, what I should have done is just leave it in the same position and do another cut, so that it would just skim off whatever the difference was from having been reattached. And that turned out to be, it was such a tiny little skim, I could barely see anything coming off, but that made the difference. Okay, so after all that, this is what we've ended up with. There is a little bit of run out there, but it's not terrible, so I don't think it's a showstopper, because the software can compensate for that to some degree anyway. So I'm just going to go with that. That's about as good as I can do, I think. The reason it's so tricky, by the way, is because the shaft, look how short it is. It's at 5mm diameter, and it only sticks out 5mm as well. And also on this end, 5mm, although you can't see that right at the moment. As far as being airtight, I'm pretty sure this joint here is completely airtight. Unfortunately, the one at the top, I don't think it is, because when I sucked on this pipe a little bit and tried to when I sucked on this here and put my finger over the bottom of that, I could feel that I was able to suck a little bit of air through, so I think it's probably in there, but just see how that goes for now. Okay, I set up a couple of other solenoids here, so in theory we should be able to try picking something up now. Alright, we've got pipes strewn all over the place now. So from the small reservoir we go through this T-junction. One side of that goes to the weenie PRU for the sensor, and the other side of it continues through this valve, through this T-junction into the nozzle. The other side of this T-junction is just open to the ambient air on that side. And I have a little piece of sellotape on here, so it's going to close that off. And to start with, I'm just going to turn it off and on, and I'll show you what happens on these lights here. So the green light means that the nozzle is open to vacuum, so it's picking something up. The blue light means that it's blowing the part off, so it's open to ambient. And then the red light means that the small chamber is replenishing itself from the larger chamber. That will be disabled during a pick though, so you should never see the red and the green at the same time here. We should need some replenishing soon. There we go. So it can only replenish when there's no picking going on. And that should be just about done. There we go, so now it just keeps picking.
So to control the switching of those solenoids from Linux CNC, we can use the digital outputs. These are just like a digital output on an Arduino. You know how you have digital write, and you set that to like true or false. In Linux CNC, you can issue an M64 command to turn a digital output on, and the P part here will be the number of the pin that you want to use. And then you can use M65 to turn it off, and you can see some examples of that. So I've turned things off and on with M64 P0, M65 P0 like that. And as it says here, it does that immediately. But there's also M62 and M63, which they do it coordinated with the next movement you get. So next time you have a G0 or a G1 command, that's when the switch will happen. So this lets you do the switching in the middle of a movement. So if you put two G0 commands, for example, and then you put this M63 in the middle of them, those two G0s will happen all in a row fluidly, but in the middle of it the digital output will switch on or off. So that's quite useful. And as for what these actually control, there are some pins. If we look at this thing again, in pins we have some called motion digital out 0, 1, 2, 3. There's only 4 by default, but you can expand this by changing some settings in the ini file. You can have a whole bunch more, but 4 is enough for me at the moment. So what I've done is I've connected these to my weenie digital outputs in my HAL file. So we've got motion digital out 0, 1 and 2, and I've labeled these nets suck and blow. So suck is the one that brings the vacuum to the nozzle, blow is the one that brings the ambient pressure to the nozzle, and they're obviously connected to my weenie outputs that are connected to the solenoids. And I'm also turning the green and the blue LEDs off, as you saw before. And then the enable refill net here, this is to inhibit the replenishing of the small vacuum chamber during a pick. We don't want to be doing that at the same time. So I've got digital output 2 is connected to that thermostat enabled, so that lets us disable the thermostat from G-code. So let's have a look at the G-code of this next little bit that I'm going to demo. I'll just look at the M65 and M64 parts mainly because that's what we've added that's new. I have a loop here that's going to do something 5 times. You can do that in Linux CNC too. It's pretty cool. So M65P2 will disable the vacuum replenishment. Well, you can see I've got some comments here to explain what's going on. So to pick a part up, we move down in the Z to -14 to where the part is. It's just a piece of paper in this case. And then we do these switchings here. We open the vacuum to the nozzle so the piece of paper will be sucked onto the nozzle. And then just for a little quick demo, we move up and then wait for a 1/10 of a second and then move back down to the same place. And then to drop the part, we need to close the vacuum to the nozzle. Then we can re-enable the vacuum replenishment from the smaller chamber, or from the larger chamber. And then M64P1, this is going to open the ambient to the nozzle. So we're allowing it to be pushed off a little bit. And then we're going to do a movement. So we have a G0, which is a rapid movement to Z0. So we're moving up 14 millimeters. Remember, we're at -14. And so we're moving up 14 millimeters, and then we're using M63 to, at that point, close the ambient to the nozzle. And then we have another G0 which moves us up to where we started originally. So what this is going to do is about halfway up the retraction movement, it's going to close the ambient to the nozzle. And I found that you can adjust this distance so that you don't have the ambient too short. If the ambient is too short, the piece of paper got stuck to the nozzle a little bit on the way up. So you can use this distance in this M63 to adjust how quickly the ambient will finish. While we're messing around with all this Linux CNC business, I thought I might show you something called HAL Oscilloscope. If anybody's still watching this video, they probably have a little bit of an interest in Linux CNC, I would think. I've never used this that much, but it seems like it could be quite useful for what I'm doing here. So you get this from this menu in Axis. So there's the HAL scope there, and it shows you a view not unlike an oscilloscope, where you would have a channel or multiple channels. You can have quite a few channels in this one actually, but the sample rate goes down. I just have my one channel and I'm sampling this at 16,000 samples at 1 kilohertz, so that's 16 seconds. And you choose your channel that you want to watch. So weenie pressure 0 is the one that we're watching here. And you also need to set up a trigger value. In this case I set it to -30, or approximately -30, which is the point at where my small vacuum reservoir will be triggered to replenish. And it sort of waits for that trigger to be triggered, and then it shows you it looks like it's showing me the 8 seconds previous and after that point, so 16 seconds total. And right in the middle here you can see the value has gone above the trigger point that I set. So this is just running the job that I showed you before, where it picks the piece of paper up and puts it down 5 times. And you can see on the left hand side, this is the idle pressure, and when I mouse over this you can see down the bottom there it says this number here. So this is what I'm mousing over, so -34. So from one pick to another we're going from -34 to -33.4, so 0.6 kPa change. So this gives you roughly an idea of how much pressure, how much vacuum is being lost for each pick. And then if you look at the shape of the pick, let's look at this one here, you can see that there's a very, very sharp loss of vacuum immediately after the pick starts, and that's because the air inside the little piece of tube between the solenoid and the nozzle itself is being evacuated. So we lose a lot of vacuum very quickly. Well, not a lot, but relatively a lot in that first spike, and then it settles to about this point here, and then when we put the paper down we get to about here. Now on this right hand side, the reason the vacuum is, or the pressure is decreasing, vacuum is increasing, is because it's being replenished at this point. So that's why in the idle time, when we're not doing a pick, the slope is going down. The main reason I did this, by the way, is I wanted to see how quickly is Linux CNC actually aware of what's going on with that pressure sensor. So from what I'm seeing here, it looks to be quite adequate in the speed that it's going to be able to manage to keep up with this. Cool, it works. And then to depressurize the system, like at the end of the day when I'm finished with it, or devacuumize rather, I can just turn the fridge pump off so there's no more vacuum going to be put into this one, and then I'll open this valve, which will make the nozzle connected to here, and if there's nothing on the nozzle of course, then this vacuum will just drain out, and then that one will drain out, and after a few minutes the whole thing will be back to ambient pressure.